Hi, everyone. Welcome to the August 2025 update of Science and Force Fields at OpenFF. The format of this presentation is I will go through some of the major projects on the OpenFF roadmap and present recent progress that we've been making towards these goals. So firstly, fitting stage 2.3, this will be the first force field that we will release with a neural network charge model. Last time I presented this slide talking about a particular candidate, which is version 6 on the images here, so the orange line. And as of June, the last update, we had finished fitting both our valence and van der Waals terms, and we were in the middle of benchmarking. It looked like the version 6 orange candidate was giving us better performance on our QM benchmarks, both on our geometric benchmarks, so the RMSD and the torsion fingerprint deviation, as well as our relative conformal energy benchmark. Unfortunately, when we got more of our benchmarks back, we saw a bit of a different story. So I've listed 3 of our 4 tiers of benchmarks here, and specifically they are physical property benchmarks, solvation-free energy benchmarks, both in water and non-water solvents, as well as protein ligand binding free energy benchmarks. And while the version 6 candidate improves on QM benchmarks, we see that on particular properties, in particular amine physical properties and non-water solvation-free energies, the version 6 candidate seems to get a little bit worse in terms of performance. We went back and we actually benchmarked a different force field candidate where the valence terms differed, although the van der Waals terms are the same. And this candidate actually showed somewhat improved performance on bulk physical properties, but we were seeing some of the same issues with AME properties and solvation-free energies. What we plan to do is, because we know that some of our users are very keen to use AshGC as a published charge model, is we plan to release this as a release candidate, but immediately start fitting a new force field candidate to actually release as stage 2.3, where we're satisfied with the performance across all tiers of benchmarks. So moving on to fitting stage 2.3 and some of the differences in the process that we're hoping will give us improved performance. We think that one of the reasons performance decreased with amine properties in particular was to do with the training data that we used for the van der Waals fitting. So in particular, with our densities and enthalpies of mixing, we realized that when we cut out properties that contain molecules that were either slow to equilibrate or had high viscosity, we actually ended up removing nearly half of our mixtures of amines and waters, as well as our heterocycles in water as well. So we've gone back to the drawing board and we've now reselected properties with a specific eye to recovering these mixtures, as well as other mixtures that had differences in representation. We still face the same issues that we did when we were filtering for the initial stage training set, where some properties with amines equilibrate very slowly. So we've now modified the protocol to allow for longer equilibration times so that we can still incorporate this data. This is currently in progress. We're currently in the middle of fitting our van der Waals terms to this new training dataset and anticipate moving on to refitting our valence terms next week. Moving on to other projects on the OpenFF roadmap, we continue to generate additional quantum chemistry data for our other projects. And in particular, we've added and completed a new training set for our lipid force field project, which I'll summarize later in the presentation. And as usual, this is run by Jennifer Clark. We also continue to make progress on our super large transition metal single points dataset. So this includes more than 600,000 calculations, and more than 500,000 of those are now complete. Another project on our roadmap that's been a long time coming is working out a long-term dataset strategy for the data that we use in training and benchmarking force fields. This project has also been driven by Jennifer Clark and is now largely complete. We have now established a standard operating procedure where we upload our datasets to Zenodo, along with a Docker container and Jupyter Notebook for recovering and recreating the datasets that we use in our force field fits. Jen has now uploaded a number of our datasets, which have been summarized in a list at this link. And in particular, I wanted to shout out that she's both released and uploaded a new version of the industry benchmark set that we commonly use for benchmarking. The industry benchmark set has been used outside of OpenFF in the general community for benchmarking force fields. So we anticipate that this will be of general interest. And this new version has filtered out a number of problematic records that we've identified, due to, for example, issues with seven-membered rings. Moving on to the lipid force field, which is being driven by Julianne in the Schertz lab. The goal of this project is to extend our small molecular parameter quality to cover lipids and membranes as well. Julianne has benchmarked the performance of our existing published force fields on both lipid and alkane properties, and found that while SAGE performs in line with existing published force fields on properties such as area per lipid and bilayer thickness, it underperforms on properties such as the order parameter quality. On alkanes, we see that while SAGE gets the heats of vaporization similar to experiment, it slightly underestimates densities, and we see much slower diffusion than experiment. So Julianne has been experimenting with refitting SAGE to lipid-specific data or alkane-specific data to improve performance on these benchmarks. She saw that while refitting SAGE to a small molecule data set with increased alkane data representation didn't change alkane parameters substantially, if she restricted the training set just to alkane data, she saw much better profiles or much closer matches of alkane torsion profiles to QM, which indicates that perhaps the force field was stuck in a different minimum in the previous fit, or perhaps the torsion parameters are not specific enough in this particular case. So she's now running some experiments to investigate these particular directions. She's also been looking at co-optimizing van der Waals and torsion parameters at the same time, but we've been running into a number of technical issues that has limited progress so far. Moving on to the protein force field, where the goal here is similar to that of the lipid force field, where we hope to extend the quality of our small molecule parameters to proteins as well. This project is being driven by Chapin in the Gilson lab. This is a long-running project, so just for a quick summary of Chapin's findings, we've previously seen that simply refitting our parameters to quantum chemistry data has resulted in force fields where the secondary structure of the protein GB3 unravels in solution, mostly the helix. Chapin has been seeing a lot of success with his recent approach of fitting force fields directly to NMR observables, where a number of iterative fits to NMR observables resulted in a force field, iteration 4, that did not unfold the helix in GB3 in long timescale simulations. Unfortunately, if we look at some of our other benchmarks, such as whether a particular peptide falls into a helix in simulation, the iteration 4 force field does not fold the peptide into a helix. So Chapin is now looking at extending the training data set to cover the AAQ-AA3 observables, and specifically starting from the optimal endpoint of the previous step, the iteration 4 force field. It's now refit a force field to this additional data. If we go back to the GB3 benchmark, we do see that this force field has now worsened performance on long timescale simulations of GB3. But on the other hand, if we go back to the AAQ-AA3 benchmark, this peptide now does fold into a helix in simulation. And now, in fact, it folds into a structure with higher helicity than AMBER14SB, our reference force field. Chapin has also been pursuing other directions in parallel, one of which is going back to our quantum chemistry training set and extending that data set with additional structures from the PDB. He's fit a force field to this extended training set, and it performs similarly to our other set of candidates. Similarly, on quantum chemistry validation benchmarks, it also unfolds the helices of GB3 in simulation and simulations of a peptide, the peptide AAQ-AA3 do not fold into a helix. However, these extended former fits, as is the working name, do give us better experimental agreement with scalar couplings in GB3 than the initial QM fits, suggesting that they might be a better starting point for the iterative NMR fitting process. So Chapin has been experimenting with combining these approaches and running fits to NMR observables starting from these former fits. And he's now in the process of benchmarking the force fields that come out. In terms of next steps, he's both benchmarking the initial QM fits to this former data on a larger protein benchmark set, as well as benchmarking the combined fits. He's also been experimenting with fitting a force field to helical conformations of a helical peptide in the gas phase, as well as continuing to experiment with replica exchange umbrella sampling approaches. So that's a rundown of some of the work that we've been doing at OpenFF the past couple months. Thank you for listening.